Hi people, this is the second tutorial that I'm making for this particular playlist which deals with buckling using the 3D Experience tool, the FEA solver, which is actually the ABAQUS program. And it's really intended for people who are either entirely new to 3D Experience or planning to transition from ABAQUS CAE to the 3D Experience platform. Keep in mind that although the solver is Abacus, but the interface and the function interface is completely different, and it is unlikely that somebody who's even fluent in Abacus can actually uh, go ahead and do certain things in the 3D experience without going through the learning curve. So my strategy for doing these tutorials is take things that are done entirely in the Abacus CAE on YouTube, and it's available there, and replicate the steps to show people how things are different when you're doing it in CAE, Abacus CAE, and you're doing it in 3D Experience platform. This particular tutorial is dealing with an I-beam. It's a linear problem, I-beam made of steel with these dimensions, and it is clamped at the very bottom, and it's axially compressed on the top. Don't let these red and green arrows fool you. They're not forces. It's just to show the axis, local 1 and 2 axis along the beam. We'll get to that later on. Now, this particular problem was done by the following professor, and it's a long, actually, this particular YouTube video is quite long. It's about 2.5 hours. But this portion of it, the one that deals with doing the eigenvalue calculation or linear buckling analysis, starts at 103 and it goes for about 20 minutes. Now, this problem this particular problem is done in that video tutorial that you see down there, video down there, is done in two stages. A linear buckling analysis, and I'm going to do that for this tutorial too. And then the second part of it is actually doing a nonlinear analysis, buckling analysis, which really uh, means that it involves Rick's analysis as you see that. So that's going to be tutorial 3, but this one is just the first portion, finding uh, uh, the critical, particular YouTube two-dimensional beam elements. Okay, now two-dimensional beam elements are not available in 3D Experience. Nothing two-dimensional is available in this 3D Experience platform. So, by the way, the length of this thing is 5 meters, made of steel. And what I'm going to do is I'm going to take beam element, model this thing with beam elements, which are just straight line, each 100 millimeter long. So there's 50 of them along the length of the beam. But what I'm going to say is that uh, because this B21 or two-dimensional linear beam element is not available in 3D Experience, what I need to do is to use B31, which is three-dimensional linear element. However, what I need to do is to uh, fix certain restraints or fix certain movement and rotation so that essentially this problem, which is done with three-dimensional element B31, becomes equivalent to the B21 element that the fellow is using. Now, it's a very simple problem as far as calculating the critical load using Euler buckling formula. If you know the value of I, and we do, you can plug it in here and you're going to get a theoretical Euler buckling load of 7.42 times 10 to the 6 Newton. Okay. Now, when it comes to doing this thing in 3D Experience, you have two choices. As far as the meshing and creating a model is concerned, it's the same. Doesn't matter which one of these two choices you pick. But when it comes to the linear buckling analysis, you can either use structural scenario creation or mechanical scenario creation. The difference between these two is certain things can be done down here, which cannot be done in the structural scenario creation. For example, explicit dynamics is not available in the first one, it's available in the second one. But for us, which is a linear analysis basically, and it's available in both the structural scenario creation or mechanical scenario creation. Now I'm going to use that top one, okay? The other thing is that when you create beams in space, basically they're straight lines, okay? So now the cross section is defined by the shape and everything, but you make a straight line, and then when you measure it with beam element, you have to tell it what the cross section looks like. And that being the case, you can actually display it in 3 dimensions so that it gives you the impression that you're really doing a 3 dimensional problem, but you're not. It's just still beam elements. So you click on the under the display tab, you click on display preferences, and there is this portion of the dialog box here which says beam symbols, and if you select solid, it will actually show it to you as a solid object. Okay, so and then if you want to see these beam orientation axis, this is direction 1, this is direction 2, axis 1, axis 2, then you check this thing. These are not forces. That's why it was kind of confusing in the first slide. So that's pretty much it. We're going to do this. Okay, let's move on to the 3D Experience platform. This is the interface, so we're going to go and do this thing as a part. In reality, it's just a line, and it doesn't matter whether you use part design or whether you use the generative shape design, it's just a straight line, so I'll use part design. Okay, and what I'm going to do is I will create a line 5 meters high. Okay, that's going to be playing the role of my the axis of the beam. So let's make a line. Well, let me make it first. Let me make a line here, and I'm going to do it from point and direction. So point and direction. The point I don't have one, so I'm going to make one. So let's see, create a point, and it's going to be 0, 0, 0 right there. So the point has been created, and the direction is going to be along the z-axis, and the length is going to be 5,000 millimeters, which is 5 meters. Okay, right there. Okay, good. Because the cross section of this thing is not a circle or a tube or a pipe, basically hollow pipe, I need an orientation point. So I'm going to create an orientation point. The location of it doesn't matter, but you have to be careful because in this particular problem, it doesn't matter because you can think about it as an I-beam that is vertically standing up and it's rotated by so many degrees. The orientation doesn't matter. That being the case, doesn't matter where I create the point, but I will create it with, let's say, maybe 200 millimeters on the x-axis. If it's too short, we can change that. Preview. No, maybe 1000. Preview. Over here. Okay, actually, let me make it a little bit longer. Maybe 2000, so that I can see it better there. So we have this point here, which is going to be used as the orientation point for the beam. And I'm using the terminology in the CATIA's FEA solver, which is Alfini. But anyway, this is all also in the ABAQUS CAE manual. Now, let's go and put some material on this thing. So tools, let's actually, let me make one. Let me make it. So create a material. And I'm going to call this thing I-beam. And today is December 1, 2023. Nothing fancy, it's just a linear elastic problem, properties of steel. Let's wait this thing for this to show up right here. You apply it to this part. Click on the green check mark, and go and input your values. So expand this thing, double click. So it's a structural, and because it's a static problem, it's just going to be abacus multiphysics, mechanical, elasticity, elastic, and the Young's modulus is 200 GPa, that's for steel, and the Poisson ratio 0.3. Okay, good. Let me save this thing. Okay, now we have created our geometry, and we're going to go and create our mesh. So we go to structural model creation, empty FEM. Here's where we create the nodes and properties. So let me click on the mesh, and here's the beam mesh. I select this, and the size of the mesh, each element is 100 millimeter. Yeah, 100 millimeter, so there's going to be 50 of them along that length, and we say mesh it, and we okay. Good. So there are these elements that are created. You can see that right there. Now for properties, because we are using beam, first you have to describe what is the shape of this thing. So you first need to go to properties section, go to properties tab. Under beam section, you see there's something called beam profile right there. Beam profile. Before you assign section, you have to create the profile shape. You click on it, beam profile 1, okay, and the shape of it is I-beam, and then we start putting in our numbers. Now I showed you in the slide what these things are, first slide. So let me start from the bottom, 10, 15, 15. Okay, so let's go here. So 10, 15, 15, and notice that this nicely shows you what you're inputting here as you do this. And this one is 300, and this is 300, and this one is the height of the beam, 400, and this is I. In other words, where is the location where actually this thing is mounted on the beam? I mean, because this is useful. Generally speaking, this is halfway through that. But if you want to apply, load with offsets and things like that, then that becomes important. And for us, it's just halfway through the height, and therefore it's going to be halfway between half of 400. That's 200. We say okay. Now we did create a profile here. It would have been nice if I call this thing I-beam, I-profile. Now we go to we click on not the profile but the beam section. You click on the beam section, you select support. Notice that the material is properly picked. A beam profile is profile 1. See that? You have to use the pull down menu, profile 1. And right, orientation. Notice that orientation is that point that I want. Actually, this, sorry, orientation geometry, you select that point, okay? And let's see what happens now. We say okay, okay, fine. That is where this guy is going to come into the picture. So under the display tab, under display tab, you select display preferences. So here's the display tab. Here's display preferences. And there it is. It says beam rendering style none, but let's make it a solid. There we are. And by the way, if you want to see that coordinate system here, direction 1 and direction 2, you click on this. It shows you that this direction, which is actually the strong axis of the bending, is axis local direction 1, and this is local direction 2. Now, this, if you think about it, it actually matches the one direction here and the 2 direction there. You see that? One, there's a 1 here, 1, 2. Okay. All right, good. Now, we say okay, we'll close that thing so we can actually see this. There's something else that you may find useful, and that is I can't remember. Let's actually save this thing. All right. So we're done here. Now we're going to go to uh, uh, structural model creation right there. You see this? Right there. You click on it. Oh, sorry. We already created our mesh. That's really not correct. We already created our mesh. So let me, we can't go there because there's already a mesh there. So we have to go to structural scenario creation. That's what I wanted, not this. This is for meshing. Structural scenario creation. And the mesh is going to be the one that I created. There. It's a structural problem. We say OK. And notice that it says there's no procedure. So you select the procedures tab and you want to do linear buckling right there. This is linear buckling or eigenvalue calculations. You click on it. It says, OK, what is the method that you want to use? I'll use the subspace iteration. That's fine. How many eigenvalues do you want? Let's say 10. And that's fine. I'll just leave this thing the way it is. I'll use the default, basically, default value. We say OK. If I'm not mistaken, that YouTuber, Dr. Petit changes that 30 to 100, but I don't think it matters in this problem. Okay, good. Now we come with the, notice that it no longer has a red exclamation mark here. So now we go and do the boundary condition. Okay. So first of all, if this is a hassle and you don't want to see this stuff, you can just go ahead and uncheck that, uncheck this thing. Uncheck this or turn it to none. The other option is just leave it there. Don't worry about it. So the bottom of this thing, the bottom of this, let me zoom in. The bottom of this is clamped, okay? If these planes are in your way, just hide them. Yeah. Okay, so we go to boundary conditions, fixed displacement. The bottom is clamped. All 6 degrees of freedom, 3 translations, 3 rotations are 0. Or I could have used clamp. That's fine. Now, when this beam to move in the direction X, I wanted to say in the YZ plane. Okay, that being the case, remember, I do not have two-dimensional element. What I have is B31, and I want to change that or make modifications so that it actually essentially become B21. So what do? I go to, again, fixed displacement. You select this line and say this line does not move. That is where the beam elements are, okay? This is just a dressing just bonus that you can see it, but the beams are actually on this line, okay? Elements on that line. So it does not move in the direction X, and rotation about Y and Z are fixed. It can rotate about X. That's how it bends. So this essentially takes that B31 element and convert it or make it behave like the two-dimensional element. All right. Incidentally, if you go here, expand this, expand element type, double click on it. Notice that there are different options that you've got. We have B33, B31, B31 hybrid, but this is the one that I want. It was the one that I want. Okay. Notice that we have boundary conditions here as we put these boundary conditions. Let me see. I have a feeling that first one, you see that first one? I have a, oh, I didn't pick it. Okay, so let's go ahead and pick it because I couldn't see it. That end right there. Okay, there it is. Now it's okay. It's no longer yellow exclamation. Okay, good, good. So this is for preventing the motion in the X direction. This is for the clamping at the end. Very good. So let's go back and apply that's pretty much it. We have to Okay, now we have to go apply our load here. So we go to loads, force on that point being the end of the beam, uh, in the direction Z, I put a -1, okay? So essentially, this is 1 Newton, and the eigenvalue that we get is going to be multiplied by this 1 to give us the critical load that we get uh, from Euler buckling formula. Okay, so I think we got everything that we need. So let me save, and then we're going to go run. I always like to pray before I run because you never know. Okay, so we go to, hopefully I didn't forget anything. So I go to simulate, model and scenario, check, basically it's a model check, no problem there. Model and scenario check, anything missing or simulation check. Critical missing obviously is going to come back and tell us what went wrong. I don't anticipate any problems here. It's almost done. Okay, good. And finally, we're going to run it. You click on iteration, gives you the monitors, the progress of the problem. Keep in mind, this is a linear buckling analysis. Later on in tutorial 3, we'll do nonlinear one. Something did not work here. Analysis phase failed due to error. We've got to find out what the issue is. I don't know where I forgot. Okay, so let me click on the diagnostic, see what it is. This is all good. This is a linear perturbation step. All loads are defined, that's fine. Okay, let's do that, Peter. Remember, let's go back there. Remember I said that the professor in that YouTube video changed the number of iterations to I think he changed it to 100. Let's go ahead and do that. Let me close this. Let's go back to this buckling step right there and change this into 100. I suspect that that was the reason that he did it, and let's go run it. We don't have to do the checks because these are already verified. So there was a reason behind that change. I did not try it myself, but now I ran into a problem. Okay, remember last time it failed. Okay, done. Extracting results. Very good. So there is your numerical calculation. Let me close this thing. There it is. This is the finite element answer to that. Okay. Now these other ones are the other buckling loads. So let's actually find out what's happening here. Let's look at the deformation displacement. There we are. Remember, for when you do buckling, this displacement don't mean anything. What is important is this number. This number multiplied by that load that I applied, which was 1 Newton downward, is going to give you critical buckle. These are the other load. Actually, let me put this thing in the front view because we know that this is not coming out of the plane. Therefore, there's no reason to look at it in 3D. So let's go ahead and look at it in view. Look at the front. There we are. This is the second mode, second buckling mode. Higher, obviously. Third, fourth, five, etc. Okay, that is the one that you want. Incidentally, because displacements don't mean anything, the stresses don't mean anything either. In the event that you want to see the beam in 3D, not as just a straight line, what you need to do is you double click on this contour, any one of these, doesn't matter, the first one, for example, and you select this third tab up here, right there, rendering. Okay, now I don't want line. If you pull it down and say profile, or profile and line, let me try profile, and then we say okay, you can see that it also shows it to you in 3D. Now this is just, it doesn't have any real value because it's just a deception that this is a three-dimensional object. So if you double click on it, let's look at the change this thing to profile and line, see what difference does it make. It really doesn't matter. In this case, it really doesn't matter. Okay, so if you go to the last row, that's the look at this. Obviously, it's crazy. Okay, when you make it display like that, obviously there's no way to escape this. It's going to happen. So here's the situation. In the tutorial 3, I will come back and I pretend that I know nothing about this buckling load. It's just that I have a beam applied to a load, vertical compressive load, and I want to see, and it may not be linear, I don't know, because if everything works linearly, then this linear buckling analysis or eigenvalue analysis makes sense. If you don't know that, you have no choice but to do a nonlinear analysis. And we're going to come back and do that, and we'll see how it goes. All right? Good luck, folks.